This is video 2.2. It deals with Newton's laws. Now the key thing here is forces predict motion. That's the key idea. Try and keep that in the front of your head as much as possible. So Newton's laws, there are three of them. The first law deals with balanced forces. Second deals with unbalanced forces. The third always applies, and it deals with action and reaction. We're also going to look at different force types. We're going to look at force combining with distance, which just gives us energy. Energy divided by time gives us power. And we're also going to think about how forces are represented and how we might resolve them or split them, combine them. And then finally we have time times force, which gives us momentum. So here we have the first two laws then. The first column here deals with the first law, and here is the second law. So the first law tells us what happens when forces are balanced. So it says when forces are balanced, objects do not accelerate. Second law says when forces are unbalanced, objects do accelerate. So this is the most fundamental way of stating it. So here an object at rest remains at rest. That's another way of saying the same thing. The blue one, we have say 10 newtons and 10 newtons. The red one is a particular example of balanced forces of 0, 0, but it's a perfectly legitimate case of balanced forces. Now over here again, this surprises no one, an object at rest starts to move. Yeah, of course, we apply a force and it's going to move off to the right. Now your common sense has a much harder time with this situation when things are already moving. So an object in motion remains in motion. Now why does your common sense not like this? Well, because you just said, oh well, balanced forces means no motion. No, we didn't say that. We said balanced force means no acceleration, and acceleration also includes slowing down. So once something's moving, there needs to be a reason for it to stop. It will just carry on at the same speed only if there's an unbalanced force, if there's a resultant force. And that's also true of the 0, 0 situation. It doesn't happen very often on Earth, but in space it certainly does. So the red one represents a probe moving along in space. Now here we've got the moving situation for unbalanced force. So as it comes in, we can see that the force is to the right, but the motion is to the left, which is a bit confusing, but really it's just slowing down. So there's a reason for it slowing down, which is that the force is opposing the motion and it is slowing it down. So really quite a tricky idea, but it's very satisfying if you get it right. So Newton's first law says when things are balanced, they do not accelerate, and that means they could be traveling at constant speed, and 0 is just another example or a special example of constant speed. Here we have Newton's third law, which says that to every action there's an equal and opposite reaction of the same type, which is the bit that people forget. So here we've got a astronaut. He pulls the rope, pulls him in, but also pulls his buddy in because it's going to have an effect on both of them. Here we see the same idea in a more earth-bound situation, well on the left anyway. If you throw a heavy object out of a boat, yes, the object will move, but you and the boat will move in the opposite direction. And here we've got an example of using a machine gun. You won't be surprised that when he fires this, he will move to the left as the bullet moves to the right. Now back to the space situation here. This guy's stuck and he's got a hammer, and he throws the hammer to the right, which will move him to the left. Now the acceleration won't be the same and the velocity won't be the same, but the force will be, and it will get him to the spaceship. Now this might seem a bit contrived, but at the bottom this is not at all contrived. This is exactly how rockets work. They take some gas. We think of gas as having no mass, but it does. It's an object, just lots of small objects, and you exert a force with an explosion or a fast burn on the gas. It goes one way and you go the other way, so you accelerate, and so you can move around in space. Now here we have some slightly technical terms that the board is using for the ideas we've just been discussing. So we've got static equilibrium, so not moving because the forces are equal, but equally we've got dynamic equilibrium, so the forces are equal but it's moving. So if you don't understand it properly, that may seem contradictory, but it really isn't. Remember that the forces being balanced just means there's no acceleration. It doesn't mean there's no motion. And finally we've got non-equilibrium, which is a long-winded way of saying it is moving, so, or in fact accelerating, which is we can see it at the bottom here. So both of these equilibrium situations are balanced force situations, and they are zero resultant force, so N1, Newton's first law, applies. unbalanced second law. Yep. So unbalanced, accelerating, first law, zero resultant force. So either there's no motion or the motion is constant. So here we've got a situation where we combine the first and the second laws. So a cannonball being blasted out. Now the horizontal situation is a Newton 1 situation. The forces are balanced, so there's no acceleration. But downwards it's unbalanced. It's Newton 2 because weight is pulling it downwards, so the effect of gravity is pulling it downwards, and that force is, we're ignoring air resistance, by the way, on the horizontal. Now the faster you fire this, the more gentle the curve will be, and eventually the curve will match the curvature of the Earth, and we call that an orbit. So here we come back to the idea of velocity mentioned in a previous video, and the idea that we can have acceleration without speed change, which it sounds a bit contradictory if we're not exactly clear on what we're talking about. So let's have a look in a little bit more detail. So velocity is made up of speed and direction. So if we've got delta speed, so change in speed, we have a change in velocity, which we're all quite familiar with. However, because direction is part of it, if the direction is changing, velocity must also be changing. That's what we can see here. So as this chap is swinging the weight round and round, the speed is very constant, but here the direction is in that direction, and here it's in this direction. So direction is definitely changing, so therefore velocity is changing. Here we have a summary of the 4 forces of nature. Now we really need only concern ourselves with 2 of them, gravity and electromagnetic or electrostatic. The weak and the strong I mentioned just out of interest. They're to do with nuclear decay and atomic structure, something we deal with at A level. So really we humans are really only aware of gravitational force, or the force due to gravity, and the electrostatic or electromagnetic force day to day. So what do they explain? Well, gravity explains falling, explains orbits, explains planetary formation, it explains star evolution, which we'll look at in other videos. And the electrostatic, contact, so when we touch a table, friction, when something slows something down, static, so attraction there, magnetism, it's a bit complicated, but it does come from the same force, as does electromagnetism. Now, a key point here is the difference in the strength is enormous. So gravity is phenomenally weak compared to the others, and that's really the key thing to bear in mind. So here we've got some examples of Newton 3 attractions. So your weight compared to the Earth is something we're really aware of, but we also weirdly give the Earth weight. So we actually attract the Earth as well. It moves a tiny bit when we move a lot, but it moves nonetheless. And here we've got electrostatics, so same situation. Here the mass is the same, so the acceleration is also the same. Now here we've got the idea of a free body force diagram. Now this sounds a bit complicated, but all it really means is you are showing the forces on one object only. So here we've got an example of someone jumping down. If we can just rerun it. So here we'll start it here. So this is a person falling, and at the moment there's only one pair. So the black arrows represent the gravitational pair. So the Earth is pulling it downwards, pulling him downwards, and he is pulling the Earth upwards. Now when he comes into contact with the Earth, we suddenly get an electrostatic pair, the red ones, and initially this is much greater, and that's why he slows down. So we can see the compression here. Think of it like a trampoline. So those arrows are really big to begin with, but very quickly they actually settle down. Now incidentally, this one and this one are equal and opposite, and this is why I stressed the must be of the same type. They are not Newton 3 pairs because they are of different type. Even though they're equal and opposite, it's only because there's a kind of a feedback between the electrostatic compression here and the weight. So exactly the same situation is shown here. We're just ignoring the Earth in this situation, and that's what free body diagram means, and it allows us to see an isolated situation and work out whether something is accelerating or not. So here we're looking at vectors, which is just an arrow really. It's a posh name for an arrow. So we've got these 2 boats here, a black one and a blue one, and if we take the black arrow there and we nose to tail it with the blue one, we get this red arrow here, which is the combined effect of those two forces. And in this particular case, we've got constant speed, so the green and the red arrow are balancing, so we have no acceleration. So here we've got terminal velocity. So we've got a skydiver, jumps out of a plane. If we start on the right here, weight is unchanged throughout the whole time, but drag does change. So these are the two forces, drag here and weight here. So there are two things that affect drag. There's speed, so the faster you go, the more drag you have. The other thing is area, so the greater the area, the greater the drag. So as speed increases, drag increases, the resultant gets less and less, till eventually the resultant is 0, and then we have this balanced situation here. So here we have weight equals drag, there we are, and you're falling at terminal velocity, the fastest possible velocity. The parachute is deployed here, and we get a very sudden increase in area and therefore drag, and that makes the resultant force strong or significant, and that slows the person down till they get to a new constant speed. It's still the drag exactly opposite to the weight, but now it's at a much slower speed. So here it's going about 60 meters per second, here it's going about 5 meters per second, so it's safe to land. Here we have the idea of inertia. So let's imagine three identical trucks, and they are differently loaded, they have different masses. So the inertia of this bottom truck is greater, so its acceleration will be less. So we can see that in our formula here. We can see acceleration is force divided by mass. Here we've got the same mass, but we've got different forces. So there's much greater force here, so greater acceleration. Velocity at any particular time is acceleration times time. So if your force is greater and your acceleration is greater, if your mass is greater, after a certain time your velocity will be greater. So here we've got a calculation of this formula, F equals ma. Again, pause the video if you want to check the calculations, but essentially we're adjusting for prefixes, doing our rearranging, and getting our answer as normal. So moving on to momentum then. Momentum is fundamentally about force times time, as I said before, and because the force is equal and opposite, and the time is also equal and opposite when two objects interact, the exchange of momentum must also be identical. So the total momentum must always be the same, so that the loss of one equals the gain of the other. So in this case we've got the blue and the red have the same mass, so once their speeds are the same they have the same momentum. So momentum is mass times velocity. It's also a vector quantity, which is important to stress, which we're trying to do here. So the rifle, assuming it can move freely, has a greater mass than the bullet, and it will move backwards, or it will recoil when the bullet is fired out the other way. So they will have the equal and opposite momentas, but that doesn't mean that their velocities will be the same, because they have very different masses. So here we have a momentum calculation. Again, pause the video if you want to look at it in more detail, but as usual we go through our steps. So now we move on to work done, which is force times distance. This is the really key formula here. Definition, these really key ideas in physics. So a small distance, as if you're dragging a fridge not very far, it doesn't take you much effort or work or energy, all mean the same thing. And the opposite here, large distance, large force is going to be more work or more energy transferred. So here we are thinking about energy. Where does that energy go? Well, as often in physics, it usually ends up as surface heat. So here we've got constant speed situation, and our graph is showing us here that the kinetic energy doesn't change, but the surface heat does increase. Now here we have got an increase in kinetic energy because this object is unbalanced, so it's accelerating, so the kinetic energy will increase in this case, as will the surface energy. So, and it's a curve, because the faster we go, the more of the energy will be transferred to heat. So here we've got a worked example again. The strongman competitions, they drag objects along. So again, the heavier the object, the further you go, the more energy that will require. So the joule is a Newton meter. It's defined as such. So if you a force of 1 Newton over 1 meter is 1 Newton meter, or 1 joule. In this case, it's 50,000. Now, power is work divided by time, or energy per time, or joules per second. So these are identical wallabies. They're going an identical height. So the work is the same. You can see that the work they do is the same, but this one has a much shorter time. So smaller time means greater power. So here we've got another more detailed calculation, and again we're looking at work. So W here divided by the time is going to give us 12,000 joules there.